see here. So I will begin with a word of prayer as I get up here. Heavenly Father, we thank you for this day. Again, I thank you for this class. Just ask that you'd be with us today, help us to glorify what we do, and to understand a little bit more about modular arithmetic to this day, Lord. In your name I pray, Lord Jesus. Amen. Okay, so I'm going to go back to the basics, prove a few things, just to make sure we're on a solid footing. So I want to talk about, the arithmetic in Z mod n. Now, remember, Z mod n for us was defined to be equivalence classes modulo n, right? And what that meant is here, x of n, it's y in the integers such that y minus x, such that n divides y minus x, right? And as we discussed, that's equivalent to saying basically things of the form x plus n times j, such that j is in the integers. There was a typo last class. I flipped the role of n and j when I wrote this down in the middle board. It was pointed out to me after class by people who noticed it during class. Thank you. You know who you are. And I also mentioned we could write this also as like x plus nz using the so-called coset notation. All right, so these are just different notations to capture what we mean by an equivalence class modulo n. Also, if another thing we can say is that if x and y are in the equivalence class modulo n, then x is congruent to y mod n, all right? So if you don't want to write brackets and you'd like to replace equalities with congruence, you can do that. And some people prefer to work more in the world of congruence as opposed to equality. Now, you have to be careful with the equivalence classes because there's all kinds of funny, funny new notations. Like, for example, if I was working in, say, Z mod 10, right? And I was to say, to simplify something like, 11,327, then in this context, what does 11,327 mean? Well, it means 1 times 10 to the 4th, right? Plus 1 times 10 to the 3rd, plus 3 times 10 squared, plus 2 times 10 to the 1st power, plus 7, right? And so you could simplify this, using the rules that I'm going to justify here in a minute. But this is the same as these are the rules of modular arithmetic we'd like to justify today. But before I justify them, I'm going to remind you a little bit about how we calculate. I'm not saying this is like an optimal calculation or anything. I'm just trying to emphasize the structure here. Namely that if we have a sum inside the equivalence class, it's the corresponding sum of the equivalence classes. So basically there's two things I'm using here. The one is that x plus y is equal to x plus y in this sense, all right? And also that x times y is equal to xy, all right? So these are definitions that I really should clarify why those are reasonable definitions, all right? But anyway, here, this is what? Well, we can also take one more step. This is actually 10, we're going to talk about this too. That's actually the equivalence class of 10 raised to the 4th power. Equivalence class of 10 raised to the 3rd power. I'm doing a lot of writing, which is just going to amount to nothing. I mean, what is 10 modulo 10? So like this thing right here, that is 0, you know? In fact, this is 0, this is 0, and this works out to 0 in the sense that, you know, it's equal to the equivalence class just containing 0. And as such, all of this just drops down to 7, right? Now, admittedly, as you can see, I got tired of writing the sub 10 on this example really quickly, right? If it would help you, we could write a sub 10 everywhere, you know, to emphasize we're doing arithmetic mod 10, but I think you guys will agree with me that this is getting really old even before I'm to the end of this example. And, all right, I can't bear it. All right, so let me get back to the foundations here. The thing I wanted to get across in this example, I failed to get across though. So here's example 2. If we're working in, let's say, Z17, right? And I look at the equivalence class represented by -2. How else could I represent this equivalence class? Yeah? 15. So how did you do that? You did -2 plus 17, because that's just adding 0 in the modular arithmetic. And so that's 15 is another way we could have done it, right? And that's not the only choice, right? We could also add another 17 to that, right? This is also the equivalence class represented by 32, yeah? Etc. So the choice of representative is not unique. Far from it, right? It's far from unique. There's infinitely many choices for a given equivalence class in terms of like the representatives, right? Because any one number in the equivalence class could be used to represent it. And, you know, it matters too, because like what if I do -2 times -2 mod 17? How's that go? Well, it's easy enough to see that this would be 4, right? But what if I had instead used 15? 15 times 15 is 225, yeah? Is 4 equal, the equivalence class represented by 4, equal to the equivalence class represented by 225? I mean, I sure hope so. Otherwise, this multiplication's not well defined, right? If we could get different results by using different representatives, we'd be in trouble, yeah? So that's what we need to stop and prove here before I forget. So this is the proposition that everything else really rests on. And here it is. If the equivalence class represented by x is equal to the equivalence class represented by x prime, and the equivalence class represented by y is equal to the equivalence class represented by y prime for x, x prime, y, y prime in z with respect to some modulus n, all right? Then, number 1, the equivalence class of x plus y, I mean, the question I was begging in example 2 is true. I mean, if you work out 225, what is it? What's the, if we divide 225 by 17, what do we get?
Remainder 4.
13 remainder 4, I heard. Yeah, so said 225 divided by, what do we say, 17. We get one of those, 95. And you said, whoa, hold on a second.
Minus 17.
Yeah, I was like, hold on. Wow. Whoa. Goodness, I better stick to proofs today. The calculations are not with me here. Yeah, 17 maybe if I'm dividing by 17, which gives us what? 12 minus 7 is 5. Wait a minute. Oh man, what is 12? 12 minus 7, 5? Okay. I don't trust myself on anything now. How many times? Oh, so 3. Agreed. So that gives us 51, which gives us a remainder of 4. So indeed, that is, remember, that's the other way we can calculate representatives for an equivalence class, is we can divide by the modulus. The remainder is a choice of representative. It's the so-called least positive residue. So like this right here, 15, is the least positive residue. All right. That is unique. There's always a unique least positive residue for a given equivalence class. Right? So there's going to be infinitely many representatives. There's one specific choice we could make that ranges from 0 to n minus 1. Right? We could do that to make it unique, but that's an ad hoc choice, which is not convenient to us as we actually do calculations, because oftentimes we don't want to work with the least positive residue. We might want to work with, instead of working with 4, with 225, you know? So, all right. My claim, though, is everything else here that we're doing really rests on this one proposition, because this proposition is necessary in order that this definition even makes sense, right? Think about this. If it was mattering which representative we used in order to form the addition or the multiplication, then we could get different answers if we chose different representatives. That would make this whole thing fall apart, right? So this is important. We must show independence of representative. This is always the case whenever you're working with what are called cosets. If you're working with if you have to add sets together, multiply sets, where it's incumbent on us to make sure that our rules for addition and multiplication don't depend on the particular element we're using to formulate the addition or multiplication, right? So how do we prove these? It's relatively easy, so I'll go through it. X equals to x prime and y equals to y prime imply there exists, let's say, j and k in the integers such that what? Let's say x prime is equal to x plus jn, and y prime is equal to y plus jk. All right? So first order of business, notice, and so we got to pick a pattern here. So let's do x prime plus y prime parentheses minus x plus y. So what am I doing right now? I'm working on number 1. All right, I'm working on the proof of 1. Now, by laws of arithmetic and z, this is x prime minus x plus y prime minus y, right? Which I can simplify as what? Let me label these things. There's a little bit of a step here, but not too much. If I call this star, and I call this star star. If we solve star and star star for x prime minus x and y prime minus y, what do we have? We've got ourselves a jn plus, whoa, dudes, seriously? You're just going to let me do that? No one sees anything wrong on the board. Yep.
Should be KN.
Yes, it should be Kn, right? This is a statement about the relation of y and y prime with respect to the modulus, which here is n. So I'm supposed to have Kn there. Yeah. Thank you. Right. So that should be Kn, which means that y prime minus y is actually, Kn. Which then we can factor the n out. We've got j plus k times n, right? Which shows us what? Thus, x prime plus y prime is congruent to x plus y. I mean, however you want to say it. Mod n, all right? More to the point, that is, means, among other things, that x prime plus y prime is equal to x plus y. All right? Because this means that the difference of these two quantities is divisible by n, right? Which is to say that they're equivalent modulo, division by n, keeping the remainder division by n. All right, so next up here, if we look at x times y, we've got x. I'll start with the x primes. X prime y prime is equal to, well, x plus jn times y plus kn by star and star star. You might have noticed I'm not doing this part of the proof the same way. You might ask why. The answer is, in the words of my little brother, Cosby Y. Let's see here. Yes, you used to ask my little brother when he's about 4 years old, what's the reason you did that, Andrew? Andrew would say, Cosby Y. And we just accepted it, because he was Andrew. Let's see here. And he was super cute at the time. Let's see here. Plus xkn plus jk n squared by algebra. Anyway, commentary from the hallway aside, what we got here? We have xy plus n times what? Jy plus kx plus njk, if you like, where jy plus kx plus njk is an integer. Thus, x prime y prime is congruent to xy mod n. Hence, the equivalence class represented by x prime y prime is equal to the equivalence class represented by xy, right? Which equivalence are we using, guys? I guess I haven't written that today. Let me write it explicitly. We're saying that, reminder, A is equivalent to B if and only if what in this context here? B minus A is an element of nz, which we could also equivalently express as n divides B minus A, right? So this is, I'm meaning this to mean A and B equivalent integers modulo n. There's a lot of different language we use here for the same equivalence because it's so commonplace, all right? So I'm trying to use a little bit of each. And then what's left is the proof of 3 is similar, right? Let me just stop here. I think this is enough for us. Proof of 3 is similar. Now, so with this all made, now we can make our definition. If we have, x and y in Zn, then x plus y is equal to x plus y, and x times y, equivalence classes here, is equal to the equivalence class of xy. This definition now is a reasonable one because of the proposition, right? We can be assured that our choice of representative doesn't endanger the specificity of the product, right? We definitely want it to be the case that when you add two equivalence classes together, you get another equivalence class, right? And now it should be clear that we do, and also that that is a specific equivalence class. Like there's no way you could get two different ones. Now that we know this, what are the properties of arithmetic mod Zn, right? What are the properties? So the properties are much like the properties were for just regular like integers. At the start of the lecture or two ago, I had this horrible pun at the start, the basics, right? All those things, all those properties of the basics, well, they're still true for equivalence classes, right? Like, for example, the addition is commutative. Why? I'll do the proof right here. We add x, equivalence class of x plus equivalence class of y, right? Plus is equal to the equivalence class of x plus y. But we know that addition in the integers is commutative, right? So I can trade that for y plus x instead. And then by the definition that's right above, I have this, right? So this gives me commutativity of addition. Nothing terribly profound here. Likewise, we can talk about commutativity of multiplication, almost the same calculation, right? So addition, multiplication commutes. We also have associativity. I won't prove that, but I'll just state it. If I have x plus y plus z, or if I have x times y times z, it's equal to x plus y plus z. These are all equivalence classes. I can't. It's hard for me to verbalize the formulas here, yeah? So we have associativity, and I haven't written, so you'd be like, you didn't write anything yet, did you? So when I talk about associativity, basically it's the statement that this makes sense. To be more specific, though, I'm saying we could group like this, right? Or we could group like that, and either way, we have the same outcome, yeah? So this is associativity of addition, and then associativity of multiplication. What else? There's an additive identity. Check this out. So x plus the equivalence class represented by 0 is equal to x plus 0, right? Which is x, which is also 0 plus x, if you like, which is 0 plus x. So there is a 0 in this set, right? So 0 is the additive identity. And how about this? If we take x plus minus x, what happens? That gives us x minus x, also known as 0, right? So the minus of x is equal to minus x. Like at each x in Zn has an additive. What's an additive inverse? An additive inverse is when you find an element that you can add to the number that you have, and you get back to the 0 of your set, right? So everything in Zn, every last one of them has an additive inverse. There's also a multiplicative inverse. What's that? Do we always have a multiplicative identity in Zn? Well, we always have a multiplicative identity in Zn. What is it? 1, right. So if I take the equivalence class represented by x times the equivalence class represented by 1. Lo and behold, I get x times 1, which is equal to x, right? And likewise, 1 times x is equal to x. I mean, once you have the, we know a multiplication is commutative. If I have, if it's working on the left, it's also working on the right if you think about it from commutativity. But anyway, let's just write it out here. 1 is the multiplicative identity. All right. Now, if given x in Zn, if there exists y in Zn such that x times y is equal to 1, then we say x inverse is equal to y, right? Of course, if this is the case, we also have y times x is equal to 1, right? And so this is a definition. Moreover, x is an element of un. This is the so-called group of units in Zn. U for units. Not every number in Zn has to be a unit, right? Not every number in Zn has to be a unit. Not every number in Zn has to have a multiplicative inverse. We've done some calculations, and I'm not sure I have time today to get into this, but the theorem is basically this. X is an element of un if and only if the GCD of x and n is equal to 1. The proof I can talk through, I don't want to write out at the moment. It's pretty simple. If the GCD of x and n is 1, then by Bezout's theorem we can find, ax plus, we can find what? Bezout's theorem gives us, ax plus bn, let's say, equals to 1 here, right? Which shows you that, the equivalence class of x times the equivalence class of a, let's say, is equal to the equivalence class of 1. That's just a proof sketch. That's essentially it. That's how we calculate the multiplicative inverse. We just find the Bezout coefficients, and the multiple of n collapses to 0 under the modular arithmetic. So as long as the number x and n have no common factors, right, except for 1, if they're so-called relatively or coprime numbers, then you have a multiplicative inverse. Otherwise, you don't. If this is not the case, then the GCD of x and n is not 1. It's some number larger than 1, which speaks to the fact there being a common factor. And if you run through the Euclidean algorithm and if you go past the last non-zero remainder to the last zero remainder, I discovered, and I wasn't teaching this before, I just noticed this in working out your homework, that if we go one step past the non-zero remainder and do the vector method, it will actually reveal to you what the zero divisor is corresponding to x modulo n. Of course, there may be easier ways to find that. For low n, it's easy to see what goes on, We don't need the Euclidean algorithm for small modulus. Like modulus 10, I don't really need Euclidean algorithm. In fact, this whole first example was very dumb. You really should be able to, and you're allowed to, you can go straight to 7 here once you're comfortable with what's going on, all right? Unless I say give a careful proof step by step or something, modulo some guiding instructions. This is a wasteful calculation. I have written far too much, in that sense. Any other properties of modular arithmetic I should talk about? Probably, but let's go on here. The one thing I think that's missing in my notes, but is always coming up in calculations, is powers. How do we deal with powers? What's the definition of a power, guys? we defined this recursively earlier, right? Like arithmetic, what do we mean by like a to the power n? I said, well, that should be a times a to the n minus 1, right? For n, an element of the integers, right? And a to the 0 is equal to 1, yeah? That was our definition for positive exponents, yeah? And so the use of n here is unfortunate. So let me change that to an m, as in mummy. All right, there we go. So likewise, if I want to calculate the mth power of the equivalence class of x, that should be the equivalence class of x times the equivalence class of x to the m minus 1 power, right? And by definition, equivalence class of x to the 0 power is just going to be, it's going to be 1, but what's 1 here? 1 here is this, yeah? In context, that's the multiplicative identity. My claim is that the equivalence class of x to the m is equal to the equivalence class of x to the m for any x in the integers and m. Although I probably should suppose that, let's not talk about 0, assuming x is not an element of nz, right? nz, by the way, is the equivalence class containing 0, right? This is not in my notes. I should have made this a homework. In retrospect, I really should have made this a homework. I guess I should have made it a problem on the quiz today, but I guess that would have been kind of mean, given that we're not done talking about this stuff yet, right? But soon, we're almost done, believe it or not. So this is an inductive claim, right? What's the base case? So I'm going to call this right here PM, yeah? So notice that P0 is true, right? Since x to the 0 is by definition 1, right? For the integers, and also by my definition of this is equal to 1, right? So that's equal to, hooray! Suppose it's true inductively then. Consider the equivalence class of x to the m plus 1, right? By definition, this is what? The equivalence class of x times the equivalence class of x to the m, right? By definition of power in Zn. And so then by the induction claim, this is what? X times x to the m by the induction hypothesis, right? Which then is what? X times x to the m, what? By definition of modular arithmetic, modular multiplication, which is x to the m plus 1, right? By definition of exponents in the integers. Therefore, Pm plus 1 is true. And the claim follows by proof by mathematical induction. So this is pretty nice. We can, take powers out of equivalence class and in, right? Out and in. Now there's a lot you can do here. You can simplify the expression inside an equivalence class using modular arithmetic, right? That's okay. That we can do. See if I can find a good example of that. Ah, yes, yes, yes. I know a good example. Do you guys ever hear of the rule of 9's? From like elementary school, do you guys remember this? Anybody? Nobody? How can you tell if a number is divisible by 9? Yeah?
If the digital sum is also divisible by 9?
Yeah, if the sum of the digits is divisible by 9. That's right. Or probably if I was in elementary school, I would have said something like, if the sum of the digits is a multiple of 9, right? So, why is that true? Why is that true? Well, that's a simple matter for us to prove in here, because we can use modular arithmetic, right? So how do we understand divisibility by 9 using modular arithmetic? What's it mean? So let's see here, example. What example am I on? 3, 4, I forgot. 3, is it 3, 4? I don't know. I'm gonna call it 3. If I'm wrong, tell me. If x is in the integers and 9 divides x, then if we look at the equivalence class of x, it's 0 in Z9, right? Now, we're talking about a rule of arithmetic, right? So we need to take a second and talk about the digital. What does it mean, digit? Like, so we have x is equal to, you know, let's say a sub k minus 1, dot, 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 a sub 2, a sub 1, a sub 0. So I'm saying that this is specifically the base 10 representation of x, yeah? What does that mean? That specifically, by definition, notation means a sub k times 10 to the power k plus a sub k minus 1 times 10 to the power k minus 1 plus dot 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 plus a sub 2 times 10 squared plus a sub 1 times 10 to the 1, right? Plus a sub 0. This is here a sub k minus 1, dot dot dot, a sub 2, a sub 1, a sub 0 are elements of the set 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9, right? These are digits by assumption. And there's a unique choice of digits that represents any given integer. Yeah? I'm not going to prove that in here, but it is true. You've been working with this pretty much ever since you've been doing math, right? This is one of the first things you have to come to terms with in like second grade or first grade or something, is like, that's what this notation means. Yeah? So, check this out. 10 is congruent to 9 plus, well, it's equal to 9 plus 1, and that's congruent to 1 mod 9, right? Therefore, 10 to the power k, let's say j, let's say m. 10 to the power m, which is, by the way, 10 to the m, is equal to 1 to the m, is equal to 1 to the m, is equal to 1. So if I take x, right, and I use this simplification, you know, well, let me not. I'm tired of writing. Let me be lazy here. Where else could I use on the board? So there's two different choices in notation, guys, here. We could use congruence up here. You know, this is congruent to a sub k plus a sub k minus 1 plus dot 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 plus a sub 2 plus a sub 1 plus a sub 0. I'm using a principle here, which is that you can make a substitution of a congruence inside a statement, and you can, like, basically you can add congruences and you can multiply congruences. I state this more formally in the notes. I'm kind of using that here. If you like, if I could write out my work, I could write out my steps like this, guys, I guess. So these were the steps I was alluding to in the very less interesting first example in class. But this is, if you want me to write out more steps, I can. Right, so this is just the definition of addition, then the definition of multiplication, and then of course all of the congruence classes 10 to the power whatever, those are just 1. So I just get AK plus the sum of the digits modulo 9. Yeah. And that's the rule of 9's. So if the sum of the digits is congruent to 0, mod 9, it means the number is divisible by 9. I think in your homework I had a question about 11. It works out a little different, right? Oh, 13. Yeah, 13's annoying. It's not as awesome. Because 13 is congruent to what? Well, I mean, okay, so your homework is also about the last digit, right? So if you want to calculate the last digit, if the same x, right? If we calculate x mod 10, everything here is 0. Except that. So if you want to calculate the last digit of a number, if we simplify it modulo 10, we can calculate the last digit. Right. If we want, the divisibility mod 11 is also interesting. Why? So like Z11, if you think about it, 11 is congruent to, well, excuse me, look at 10, Z10, 11 in Z10 is congruent to 1, right? Not 1, my bad. Oy. Sorry, I'm thinking about something, and oh, yeah, 10 is congruent to 11 minus 1, right? Oh, I'm sorry. My brain's not working. Let me go on here. If you guys ask me a question, I can answer it. But I'm trying to pose a question to answer, and I'm not posing the question right. So it's like I can't fix that in my mind at the moment. Let's go on here. Let's see here. So, yeah, what if we wanted to study divisibility mod 11? I guess that's the question I was trying to come to. So if we wanted to see, does 11 divide x, right? That would be only true if the equivalence class of x mod 11 was 0, right? And if you were to study that question, with respect to the base 10 representation, you'd end up wanting to understand what is 10 to the power m congruent to, what is that mod 11? So what is 10 with respect to mod 11? Well, we can also write this as minus 1 to the m, right? So there's a similar rule. It's not the rule of 9's, but to study divisibility by 11, you'd end up looking at like an alternating sum, like the plus the digit minus the digit plus the digit minus the digit kind of thing. Let me be specific here, like example 4. Let me just be specific here. Let's look at 3,217. Does Does 11 divide, 3,217? I mean, probably not. But here's the one way we could do that. 3217 is equal to 3 times 10 to the third plus 2 times 10 squared plus 1 times 10 to the first power plus 7. And 10 is congruent to minus 1. Well, let me just get straight to the point. So this is minus 3 plus 2 minus 1 plus 7 in 11. Because 10 is congruent to minus 1. And minus 1 to an odd power is minus 1. Minus 1 to an even power is what?
Positive.
Yeah, positive. So what did we get there? I think we got a 5, right? Which means that, no, 3,217 is not divisible by 11, right? All right. Let me work on something a little bit more crazy. What if we wanted to know what is the ones digit in, I don't know, 5 to the 100 power. So you can't use your calculator to calculate 5 to the 100 power. It's just too big, all right? I mean, you could. It'll give you an approximation to it, probably. But you're not going to be able to see the last digit, right? Because you got like 12 digits, maybe 13 digits. You're like, I've got the Wolfram Alpha app. I got as many digits as you want. Fair enough. But we're not talking about that. You know? It's the most amazing thing. Everyone's doing so great on their online homework now. How'd that happen? We just teach so much better in the last 2 years. It's the weirdest thing. So this is the question. Is the generative AI, is it helping students learn better, or is it just doing the assignments for the students? You and I both know the answer to that. And I think it's embarrassing that I can't get a straight answer out of many instructors. Most of the instructors I know here would say it is doing, like the students are using it to do the problems, obviously, right? Like there's a subset of students who are using AI responsibly to learn better. But there's a much larger collection of people who are no longer giving money to Chegg and are now just using the free AI, right? Let's be honest about the need. Well, anyway, I'll shut up. So if you think about this, 5 to the 100 is equal to, some number. It's got k digit, k plus 1 digits, right? Right, there is some decimal expansion of 5 to the 100, and it should be clear to you guys that if we were to look at that modulo 10, that would pick off the ones digit. So to answer this question, it suffices to reduce this number modulo 10. How can we do that? What do you guys think? There's no one right answer to this question, guys. Well, excuse me, there is one right answer to the question. There's no one right way to do this problem. All right, there's different ways you could parse the arithmetic here. Like, let's see here. Actually, I may have picked something really dumb in picking 5. 5 might be too easy, guys. I think 5 you probably could just figure out by patterns. Oh man, son of a gun. Let's not do, is it too late? I guess I'm stuck with this. Like if we calculate 5 squared, we get what? 25. We calculate 5 cubed, we get what? 125. We calculate 5 to the 4th, we get 625. Noticing a pattern, 5 to the 5. Blah, 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 5. All right, so this is 5. Let's stick a fork in it, it's done. All right, that wasn't a proof. Let's do something harder. I'm sorry, poor choices on my part. How about 6 to the 100? Ha-ha! Now we're in trouble. What's the 1's digit in 6 to the 100? All right. So, faced with something like this, I could trade it for 6 to the 100, right? And why work with 6 when you can work with -4, right? You know, we're working mod 10 here. And let's see here. So I guess I could do, I don't know. Of course I can eat the minus, right? Because -4 to the 100 is 4 to the 100, yeah? Which is, oh, I don't know. Let's see here. 4 to the 10 to the 10, which is, you know what? I like 2 to the 10. Oh, my bad. I got to start making some. All right. Let me make it smaller here. This is 4 to the what? I'm sorry, guys. Let me. I'm running out of board space if I'm not careful. What if I did something relatively simple, like 4 to the 4 to the 25, right? I could do that, yeah? Because 4 times 25 is 100. 4 to the 4 is what? 256. Which is, by the way, 6, because we're working mod 10, right? Mod 10. So then I've worked my way to 6 to the 25, which, let's see here, I could do that as like, let's peel off a 6 to the, I don't know, what do you guys want? 6 to the 5th? To the 5th, okay. What is 6 to the 5th? You guys got a calculator? This you can calculate, right? 7776. Really? It's that? Really? 6 to the 5th is 7776? Whoa. So 6 to the 5th plus 1 is 7777. I like this. I'm going to remember that. Thank you. So this is actually 6 to the 5th, which is apparently 6 to the 5th, which is 7776, which is 6. So the answer is 6 is the 1's digit. You guys have a calculator, right? So I think a good approach to these problems is to like pick off a fairly big power, find the 1's digit for that, and kind of work with that. The alternative way to do it is just to try to keep making it like smaller and smaller into finding numbers that you can kind of manage with basic arithmetic. There are more strategic strategeries for this kind of problem. Yeah, would I do something wrong?
No, it's correct. I'm just saying, like, you know, for the 5 one, you just showed that you're getting the pattern.
Yeah.
The pattern a lot for the 6.
Ah, well, I didn't want to know about that. So that's not really, I would like for us to use these problems as a laboratory to study modular arithmetic. But yeah, I should have done something like 7. Is 7 bad? I don't know. Although that's probably an interesting question in its own right, is like, what is the 1's digit when you look at a number to a power, you'll probably see that there's some kind of like reappearing pattern of digits there. That is the kind of question that we could study in number theory. But I say we, I don't mean me, because I don't typically teach that course. At least not lately. I think I taught it like twice back in the day. Okay, so any questions? So modular arithmetic is, I think, interesting in its own right. We can use modular arithmetic to study questions of divisibility. So if you look at the notes, I have some further examples about like zeros of polynomials and things. I don't think I've asked you any homework on that, so I'm not going to spend class time on it. There's much more to learn here, all right? I think it would be good for us to maybe spend the last example here just on a specific example of Zn, and let's just put it all out in front of us so we can appreciate like the whole story. And we'll make it small enough that it's interesting, but big enough that it's not just dumb. I think Z12 maybe is a good example. So let's look at arithmetic mod 12. So the set of least positive residues here, and we have finally reached the end of my discussion of modular arithmetic. This is the time I will admit to you guys that in fact, in practice, we don't use the brackets because they're really, really annoying. So instead, we do this. Right? And we write things like 12 is equal to 0, is equal to 24. 1 is equal to 13, is equal to 25, is equal to minus 11, etc. So at the start of this, I say I'm working modulo 12, right? If this is too freewheeling and careless for you, if you're more of a math legalist than I am, if this really is unsettling to you, you may use congruence and become completely rigorous to your heart's desire, all right? But obviously, this is what you'd like to do calculations in, right? You don't want to have to write bracket, 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 bracket when you're actually doing things, right? Those are helpful for us to get started with, because now you got to understand that when I write 1, what I mean is 1 plus 12z, right? This 1 is actually a set of integers, right? It's an infinite set of integers, right? We can partition the integers into 12 equivalence classes with respectively least residues of 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, all right? Which one of these are units? My claim is that U12, the set of numbers that have multiplicative inverses in here, are the numbers which are relatively prime to 12. Those we can figure by basic arithmetic, right? The prime factorization of 12 is what?
2 times 2 times 3.
Yeah, 2 squared times 3, right? So if any number doesn't have a common factor of 2 or 3, it's relatively prime to 12. So what you're looking at, you got 1, 1's always in there, 2 is out, 3 is out, 4 is out, hey, 5. 6 is out because it's got a 3 in it. 7, we like 7. 8 is out, it's got a 2 in it. 9's got a 3 in it. 10's got a 2 in it. Oh, 11. So this is the group of units modulo 12. Everything else, right? Everything else, these things, 0, 2, 3, 4, 6, 8, and 10. These are all, what's that?
9.
Oh, thank you. 0 divisors. Let me explicitly show you, like 3